rotary atomizer will produce the spray droplets by the centrifugal energy, by the rotation of the atomizer, and not by pressure, as with a normal hydraulic nozzle. In a hydraulic nozzle, it's the pressure of the liquid from the pump that produces the spray droplets. And then the droplet size will depend upon the characteristics of the nozzle, the pressure, and the airflow over the nozzle, which is proportional both to the speed of the aircraft and also to the orientation of the nozzle. In the case of a rotary atomizer, the only function of the pump is actually to deliver the liquid to the atomizer. After that, it's the rotation of the atomizer that breaks the spray up into droplets. You can compare the production of the droplets to a dripping tap. Now, if you look at the end of a tap when it's dripping, you'll see that the liquid comes down, it forms a ligament, the drop breaks off, another ligament comes down, another drop comes off. And in each case, the drop is approximately the same size. Now, on the rotary atomizer, much the same thing's happening. On the surface of the woven cage, you have the crossings of the wires. So the liquid will stream off the crossing of the wire, form a ligament that will then break off as a droplet. But because the atomizer is rotating, you've got the centrifugal force stretching that ligament, and therefore everything happens much more quickly, there's much more energy being put into it, and the droplets that are formed are a lot smaller. So instead of a big drip from a tap, you get a small droplet. But the actual size of the droplet depends upon the rotational speed. So the faster the atomizer is turning, the smaller the stray droplets you produce. Or if you want to produce bigger droplets, you slow down the atomizer. Now, with this AU5000 atomizer, the speed of rotation is determined by the angle of the fan blades and also by the forward speed of the aircraft. So if the fan blade is near enough in the feathered position, the atomizer will be turning slowly. If, on the other hand, you adjust the fan blade to be more flat to the airflow, like this, then the speed will increase and the droplet size will be smaller. Although I've said that the rotational speed depends on the blade angle, it also depends upon the airspeed and it depends upon the type of fan blade. Now, actually, we supply 3 different fan blades. The one on this atomizer is the standard version, which would typically be used on piston-engined aircraft. On fast turbine aircraft, we have a shorter fan blade, which is also used in conjunction with the deflector plate on the gauze. And for helicopters or very slow aircraft, we have a longer fan blade. But for a given fan blade, the rotational speed will depend upon the angle and the airspeed. Now, the majority of forestry work is done with turbine aircraft, and the rotational speed would be higher than that for agriculture, because typically, although in agriculture we're shooting for a droplet perhaps around about 200 microns, in the case of forestry it's smaller, typically in the range of 100 to 150. Therefore, it's the same atomizer, but set to run faster. We have an option of an air deflector plate which is mounted ahead of the gauze. And the purpose of that is to deflect the air away from the surface of the gauze, because at high speeds the production of the droplets, as these ligaments disrupt, can be influenced by the airflow over the atomizer. And the result can be that the air just literally rips the droplets off as they're being formed, and you get a less good spectrum, and also you tend to get smaller droplets. On the other hand, if the air is deflected away from the gauze, then you're producing the droplets in a regime of much lower axial velocity, and they'll have time to form before they're released into the airflow. So that's an option that we do recommend for fast turbine aircraft, especially in agriculture, where you're trying to produce, compared to forestry, relatively large droplets. However, for forestry, it's not so important. And if you're doing specialized work like mosquito control, public health applications, where you actually want very small droplets, then you'd still use the standard configuration. We've contracted a lot of wind tunnel testing ourselves in wind tunnels. and many organizations, research organizations, agrochemical companies, governmental agencies have also conducted their own tests, and there are now several tunnels around the world that are able to do this work. All of them use a similar technique. They use an instrument to measure the droplet size downwind of the atomizer. So they put the atomizer in the wind tunnel. They'll operate it at an airspeed typical of the aircraft, be that of a piston engine type or a turbine type. Then a distance of perhaps anything between about 3 and 6 feet downwind from the atomizer, they'll use a droplet size measuring device to record the actual size of spray droplets that are being produced. Now it's important that that's relatively close to the atomizer, so those are the droplets that are actually being made, and there hasn't been time for any evaporation to take effect. Typically those instruments are laser droplet size devices, and they work by shining a laser beam through the spray cloud, and it's the diffraction of that beam which is then recorded by a sensor and then processed by a computer to give a true measure of the droplet sizes. Although cards are very useful to see what's actually arriving at crop level, there's obviously things happening between the aeroplane and the crop. Possibly there's evaporation, possibly there's a winnowing effect where the smaller droplets are carried away further than the bigger droplets, and all of that can skew the results on individual cards. But when you're using a laser device that's actually traversing right through the whole spray cloud, you're measuring exactly what's coming out of the atomizer. And of course, the same wind tunnels, the same measurement techniques are also used with conventional hydraulic nozzles. So that way it's possible to make an accurate comparison between what comes out from a rotary atomizer and what comes out from a hydraulic nozzle under the same conditions. The initial starting point should be about 2/3 of the total wingspan. Not the distance from the wing root to the wing tip, but of the total span of the aircraft. It does differ to a certain extent between aircraft, but a good starting point is 2/3 of span. When we come to actually do flight tests, to look at the vortices, which is best done actually with a camera on the ground and also cameras on the aircraft, if we see product being entrained in the vortices, then the atomizer should be moved in. If, on the other hand, there's no sign of any wingtip vortices, then it's possible to consider moving them out a bit. But that will depend also on the size of the spray droplets that we're producing. If you have an aircraft set up to produce small droplets, there's more risk that they'll be entrained into the vortices than the bigger droplets that are falling quickly and out of the vortices. So it depends on the airplane, and it depends on the intended configuration. In forestry, very often we're not so concerned about drift because we're spraying enormous areas with small droplets, typically of an ultra-low volume product, which is formulated in an oil and is not volatile. And in forestry, it's quite normal to go out beyond the 2/3 of span and to accept that there will be some product thrown into the vortices and potentially drift a bit. But then again, those aircraft are operating at much wider track spacings than is the case in agriculture. So very often you will have a different setup between forestry and agriculture. Normally, I would say apply at a similar height to conventional hydraulic nozzles. You have to remember that with the slightly smaller droplets under windy conditions, there is going to be possibly more lateral displacement with the wind. So perhaps you have to be more careful adjusting your flying height to the wind than you might be with bigger droplets from hydraulic nozzles. As I said, every drop that's produced from the atomizer is quite close to being of a standard size. Now we describe the spectrum, the range of droplet sizes, by the ratio of big droplets to small, or the difference between big droplets and small droplets compared to the mean size. An ideal atomizer would produce all the droplets of the same size exactly. In practice that can never happen, But what we're shooting for is to get as tight a spectrum as possible, so that as many as possible of the droplets, and especially as much as possible of the volume of the liquid, is contained in droplets close to the optimum size. We call this controlled droplet application, CDA, which is the way we describe a spectrum which is a lot tighter than you would get from a traditional hydraulic nozzle. Now, the important thing about this is that we're both reducing the volume of product in the big droplets and also in the small droplets. Now, in the case of the big droplets, they can be very wasteful of volume because there's a relationship between the diameter of the droplet and its volume. Because a droplet is a sphere, its volume is proportional not to its diameter, but to the cube of its diameter. So that means if you make a droplet twice as big, it's not twice the volume, but it's 2 times 2 times 2. It's 8 times the volume. So it contains 8 times the product, and it's also 8 times heavier, so it falls a lot quicker. So even a few big droplets can be very wasteful of product and result in poor coverage. And especially if you have a fairly open crop where there's a lot of, from a vertical perspective, there's a lot of soil visible, there's a pretty good chance those big drops are going to land on the soil and not come in and be filtered out by the foliage. So for that reason, big droplets are wasteful and they have a big impact on coverage. At the other end of the spectrum, the small droplets, because they're lighter, because they're settling more slowly, they've got a greater risk of being entrained in the vortices, the wingtip vortices of the aircraft. They are the ones that are liable to cause drift. And also we want to minimize the volume of product contained in those driftable droplets. Another factor is evaporation, because in conditions of high temperature and low humidity, there's always the risk that the smaller droplets will evaporate. That's because a small droplet has a bigger ratio of its outer surface area to its internal volume. Therefore, it's more prone to evaporation. There's more exposed surface. And of course, as it evaporates, it gets lighter, so it sediments more slowly or gets entrained more in vortices or turbulence, hangs in the air for longer, evaporates more, and eventually virtually disappears or drifts completely out of the spray area. So it's very important that we minimize the volume of product in these small droplets. So this is achieved by a tight spectrum, and that's what we mean by CDA. Here I have a table tennis ball, and here I have a tennis ball. And the tennis ball is approximately twice the diameter of the table tennis ball. So you might think that it's also twice the volume, but that's not the case, because the volume is proportional to the cube of the diameter. So if we make it twice as big, we make it 2 times 2 times 2, which is 8 times the volume. So the volume of product that's contained in this one tennis ball is exactly the same as the volume of product that's contained in these 8 orange table tennis balls. So from the same amount of liquid, instead of producing 1 drop, we can produce 8 drops. But of course, also, it is 1/8 of the weight. So its settling velocity is going to be less than the heavier tennis ball, whereas that's going to fall quickly, this is going to fall relatively slowly. But by falling more slowly, it's also going to have the opportunity to be displaced sideways, and as I mentioned earlier on, to be filtered out into the foliage, rather than, in this case, dropping straight down onto the ground. But that is what sets the lower limit to the droplet size, because we need to pick a size which will fall in conjunction with the wind, in conjunction with the turbulence behind the aircraft, within the swath. It wants to be displaced within the swath, it wants to give the good coverage, the good penetration, but not to be so small that it drifts right out of the canopy. Well, it's important, first of all, to explain actually what the volume median diameter, the VMD, means. If you took all of the droplets in the spectrum and you put all of the droplets bigger than the VMD in one bucket, and you took all of the droplets smaller than the VMD and put them in another bucket, then you would have an equal volume of product in each bucket. Not an equal number of droplets, that's a different thing, that's the NMD, the number median diameter. But for the volume median diameter, all it's telling you is that that's the dividing point above which you've got half the droplets and below which you've got half the droplets by volume. But it doesn't tell you anything about the sizes of those droplets that are below the VMD. In the case of a rotary atomizer, where you've got a narrow spectrum, more of the droplets are close to the VMD. It's because it's a narrow pattern to the spectrum. There are relatively few droplets on the small end, the tail of the spectrum. However, if you've got a hydraulic nozzle, that spectrum is much flatter. Therefore, the volume of those droplets below the VMD, which is contained in very small and drift-prone droplets, is a lot greater. So for that reason, although with the rotary atomizers we're typically producing droplets with a smaller VMD, we're not necessarily producing droplets where we've got a higher proportion or a higher volume in the driftable range, because even those droplets that are smaller than the VMD are closer to the VMD, and those at the very small end are contained in a much lower volume. We have to remember that when we reduce the applied total volume, for example, from 3 gallons an acre to 2 gallons an acre, we're not using less of the formulated product, not using less of the active ingredient. We're using exactly the standard label rate of active or formulated product per hectare, but we're mixing it in less water. So ultimately, we're still applying exactly the same amount of product to the crop, but using smaller droplets, and therefore getting at least as many droplets and at least as good coverage and probably better penetration than if we had a higher volume contained in bigger droplets. I would say, in my experience, probably well over half of the agricultural aircraft operating in South America are using rotaries of one type or another. And that's mainly for fungicide, a certain amount of insecticide. They're not generally used for herbicide, but you wouldn't expect that anywhere. But especially in the large monocultures like the soya, it's become pretty well the established technology. And indeed, many, many more of the products are labeled for low volume application, either specifically for low volumes down to perhaps 10 litres, 20 litres a hectare, which is the same thing as 1 or 2 gallons an acre, or increasingly labels just mentioning a droplet size that's appropriate for giving the proper application and the proper coverage, which then leaves it to the operator to use whatever technology is going to give the best results. I think one of the reasons has been the need for higher application volumes in terms of the labeling of the products that are applied. Because there's a huge difference between some countries. I go back to the example of South America, where the same active ingredient, very often from the same manufacturer, has a label for low volume application, which normally means CDA techniques. Exactly the same product, often under the same trade name, is sold in North America with a label prescribing much higher volumes. And it's not practical to apply those higher volumes using rotary atomizer technology. Now, what's happened in the last few years in the States is that especially some of the fungicides have now got labels for lower volumes, such as, for example, 2 gallons, and operators are finding it necessary to use rotary atomizers to apply them effectively. Well, if we're talking about northern Brazil, near to the equator, obviously that's nothing like Canada. I mean, there it's hot and humid and it's a tropical climate. But Brazil is an enormous country, and below Brazil you've got Argentina. So you have the complete range of climates, from the hot, humid, tropical, all the way down to the temperate climates in the southern parts of Argentina. And the techniques are used right through that region. So among that, you have very similar conditions to those in Canada. And it isn't as if the technique only works in one part of that region. For example, it would only be used in northern Brazil or only in southern Argentina. It's used right across. And the fact remains that it's the smallest droplets that are the most prone to evaporation, as I said earlier, because of the ratio of the surface area to the volume and the fact that they are the ones that are sedimenting more slowly and have got more time to evaporate. Now, the small droplets from the very wide spectrum of a hydraulic nozzle are going to evaporate even more than the smaller droplets from a rotary atomizer, which are close to the desired droplet size. So it's a factor you have to consider with both technologies. But the fact remains that as you come down in application volume, in order to achieve the coverage, you are inevitably reducing the VMD. You are reducing the size of droplet which you require to get the coverage and to get the penetration. So in countries such as in South America, where this technology is widely used, in more extreme conditions of higher temperatures and lower humidities and lower application rates, not forgetting they're often down to 1 gallon an acre, not 2. In those places, it's normal to add a spray oil, an emulsifiable spray oil, as an adjuvant to reduce evaporation. And that's also got the advantage that it acts as a sticker when the droplet arrives on the foliage and gives improved rain fastness of the spray. So if you get rain or heavy dew on the foliage, there's less likelihood of it being washed off. So there are advantages in oils, both from the point of view of the transport of the droplets, preventing evaporation, but also from the sticking on the foliage. If you just go for more and more volume of an increasingly dilute product, because you're still putting on the same amount of active per acre, and putting it out in bigger and bigger droplets, you're getting wonderful coverage of the top of the crop, which may even be running off, but you're not reaching the areas where potentially the pest or the disease is living. I think the only exception, I'd say, to that is if you're operating in very hot, very dry conditions, and you're using a low volume without any adjuvant, and you're into a situation where you're getting evaporation. But the solution to that isn't necessarily to go up in water volume, but perhaps to consider using a spray oil to reduce the evaporation. Five litres per hectare, which is a third to a half of a gallon an acre. Now, at such low rates, you need quite small droplets. I mean, you may be somewhere in the perhaps 50 to 100 micron droplet size range. And if you were to do that with a water-based product, you'd have huge problems with evaporation and drift. So ultra-low volume spraying is normally only done with ready-to-use formulations which are formulated in oil or an involatile solvent. Now, that technique is widely used for specialized applications. For example, a lot of the forestry in eastern Canada, that's done with oil flowable formulations at around about 2 to 3 litres a hectare, typically about approximately a quarter of a gallon an acre. But that's in big areas where drift isn't a huge concern, but coverage, efficacy, penetration, productivity of the aircraft are all vitally important. In agriculture, there are virtually no formulations, well, probably no formulations in Canada. Worldwide, there might be a few, which are still used at ultra-low volume for agriculture. Other applications, for example, grasshopper control, locust control, mosquito larvicides, water-applied larvicides, those are put on at these rates. But if we're talking pure agriculture, the answer is no. So generally, we'd be using a water mix product. We'd just be using exactly the same emulsifiable concentrates or whatever as would be applied at the high volumes, but with less water, the same amount of active ingredient per acre. And if we keep our droplet size under control, such that we don't run into a problem with evaporation, that's a perfectly acceptable technique. But we've got to accept that there is a lower limit that's possible without the risk of evaporation and drift. Coverage, we're just talking about the number of droplets, or the volume of product in the droplets that's delivered by the droplets. So we could have a lot of big droplets of dilute product, or we could have a lot of small droplets of more concentrated product with the same amount of active but in less water. Now those big droplets are going to tend to land on the first surface that they encounter. They're not going to be subject to any deviation of their trajectory due to wind or turbulence behind and below the aircraft. So they'll tend to impact on the upper or the outer parts of the foliage. On the other hand, the smaller droplets are going to be much more subject to any air movement, and therefore they're going to much more easily penetrate a dense canopy. You can think of this a bit like when it begins to rain with big raindrops. If you stand under a tree, you'll be dry for a while because those drops are landing on the crown of the tree, and only when the tree gets completely saturated do they start dripping through. On the other hand, if it's a misty day with a very fine drizzle, you're not going to keep yourself dry under the tree because that fine mist, that drizzle, is going to go everywhere. It's very similar on a smaller scale to what's going on inside the plant canopy. The other thing to consider is actually the form of that canopy. You might sometimes be spraying a fairly dense crop where the majority of it is horizontal or somewhere near horizontal, perhaps like the leaves of potatoes. On the other hand, you might be spraying a canopy or a crop which is largely vertical, such as early wheat, for example. Now, in those cases where you've got a very sparse canopy, if you look at it from above, what you'll see is mostly soil, and you'll just see the vertical part sticking up. Now, if you look at it from the perspective of a droplet coming down from the aircraft, if it's a big, heavy droplet falling more or less vertically, there's a very good chance it'll just hit the soil and be wasted. On the other hand, if it's a smaller droplet, which is moving obliquely, either with the wind or the turbulence behind and below the aircraft, it's got a much better chance of being filtered out by those vertical parts of the canopy. So you're going to also get, it's not so much penetrating a dense canopy, but it's getting coverage on a difficult to reach surface. Cards give you a very good indication of what's arriving where the card is. Now, you have to remember two things. First of all, the cards are normally above ground level, perhaps about 3 feet above the ground. Therefore, this is a spray cloud which is free to move over an open surface. In a real crop, especially a well-developed crop, you have a much rougher surface, a much aerodynamically rougher surface. So the interaction of the crop and any wind or turbulence behind and below the aircraft might give a different deposition on the crop to what it gives on a card. But as a first approximation, a card is very useful. But we have to remember that the actual trajectory of the droplets is going to depend upon the size of the droplet, how quickly it's falling, also upon any wind or turbulence. So there's no saying exactly which direction the droplet may be going. The bigger droplets might be falling vertically, the smaller droplets might be moving more closely to the horizontal. So for that reason, especially when you're using relatively small droplets, I don't like the idea of using only a horizontal card. Because if you have a horizontal card, the small droplets might skate over it obliquely and not impact. On the other hand, if you used a purely vertical card, the big droplets might pass it. So for that reason, it's a good idea to use an angled card, as we've been doing in our tests here, typically at 45 degrees. So you have a collecting surface that works both for the droplets moving horizontally and those that are moving vertically. If you have an outbreak of a pest or a disease that favors a particular crop or particular conditions, it's going to spread very rapidly. Now, if you have isolated fields, so you have one block of soya, one block of something else, and then soya many miles away, it may well take a long while to spread. When you've got adjoining fields, a whole contiguous area of the same crop, it can just spread like wildfire. And the only way to stay ahead of that is to have a very productive spray operation that can cover the maximum possible acreage in the minimum time. Also to remember that, especially with diseases, they tend to occur in hot and humid conditions, which is very often after rain. And after rain, it's possible that the fields can be so waterlogged that it's impossible to get in with ground sprayers. So very often aerial spraying is the only way to control the problem. The reason is that especially on fast turbine aircraft, there is actually an upper limit to the size of droplets that you can easily produce. And this is due to the airflow over the atomizer. With slower piston-engined aircraft, it is feasible to produce larger droplets, but there is still an upper limit to what you can realistically achieve, certainly in the air, with a rotary atomizer, because of the airflow over the atomizer, and also just introducing the droplet to the moving airstream over the aircraft. Although actually in ground applications where we don't have this issue of the airflow, then the rotary atomizer technology is widely used for herbicide application. I mean, indeed in Micron we have quite a few products specifically for that. But the difficulty is with the fast-moving air.